In this video, I'll be explaining about dynamic programming using top-down approach, that is with the help of memoization. In the previous video, I had explained about dynamic programming using a bottom-up approach. To solve a problem using a dynamic programming approach is to create the sub-problems of a problem using a recurrence relation and then solve each sub-problem only once, record the results of the sub-problem, that is solutions of the sub-problem, into a table, and then using this table you get the solution to the entire problem. In the previous video we had seen that in top-down approach the problem was divided into sub-problems, but the sub-problems were solved more than once. So I pasted the code from the previous video. So I have the top-down approach to calculate the Fibonacci, and the example I took was Fibonacci of 5. So if n is less than 1, then return 1, else calculate the Fibonacci of n minus 1 and n minus 2. So it's just the splitting of the nodes. And then we observed that few of the sub-problems were solved more than once. For example, Fibonacci of 2 was calculated here, Fibonacci of 2 was calculated here, and Fibonacci of 2 was calculated here. So the problem was divided into sub-problems, but the sub-problems were calculated more than once. So in this video I will show the top-down approach but with the dynamic programming concept, that is top-down approach with memoization. The difference between the top-down approach with memoization and a top-down approach without memoization is in the top-down approach with memoization we have a table or an array which is called here as a memory, and then we use this to store the results of the subproblems. So if I see the code of top-down approach with memoization to calculate the Fibonacci compared to the normal top-down approach, we see this part of the code, that is calculating the Fibonacci, is same in both the cases. So if n is less than or equal to 1, here we say return 1, but here we store the results to the table. Else Fibonacci of n minus 1 plus Fibonacci of n minus 2, the same thing, but here we return, but we store the results here to the table. We calculate the Fibonacci, that's this part, only if we have not calculated it before. So if the solution is not available in the table, then calculate Fibonacci, otherwise just return the result. So I'll take the same example, Fibonacci of to calculate Fibonacci of 5. So Fibonacci of 5 using memoization. So if I say this one, we have a array. So I'll draw the array here. So array will have 0, 1, 2 till 5. So initialize the memory. So I call this array as memory, and then in initialize memory assume that we put all the elements of the array with -1. So -1 indicates that we have not calculated the Fibonacci until now. So we'll calculate the Fibonacci for 5. So Fibonacci of 5 is nothing but so Fibonacci of 5 in the table is still -1, so this is 5. So we go into the calculation mode, and then 5 is not less than 1, so we go to the else part, and then memory of n is equal to Fibonacci of n minus 1, so it's a recursive call, so we call Fibonacci of 4, and then we have to do a plus Fibonacci of n minus 2, that is 5 minus 2 is 3, Fibonacci of 3. Fibonacci of 4, again we have not calculated the Fibonacci of 4, so we do a Fibonacci of 4 minus 1, that is 3, and Fibonacci of 4 minus 2, that is 2. And then Fibonacci of 3, now again Fibonacci of 3, we have not calculated any Fibonacci till now, so we calculate it to be Fibonacci of 2 and Fibonacci of 1, and Fibonacci of 2 is also not calculated yet, so I'll move this table here for convenience. So Fibonacci of 2 is not calculated yet, so I have to do Fibonacci of 1 and Fibonacci of 0. So if we look at the code, so Fibonacci of 0 and Fibonacci 1 is not calculated yet, but if n is less than 1, so if less than or equal to 1, so if 1, in the case of 1 and 0, the table will be filled with 1, so this will be 1 and this will be 1, so Fibonacci of 0 is 1 and 1 is also 1. Fibonacci of 2 will be Fibonacci of 1 plus Fibonacci of 0, so it's 1 plus 1, that is 2. So Fibonacci of 2 is 2. So we are updating the table. And then Fibonacci of 3 is Fibonacci of 2 plus Fibonacci of 1. So Fibonacci of 1 is already 1. So if we see a call now, so Fibonacci of 3, Fibonacci of 3 in the table is minus 1, so we go inside and then we see, okay, n is less than or equal to 1, so 3 is not equal to 1, so we go to the other part, and 3 is equal to memory of 3 is equal to, so memory of 3 is equal to Fibonacci of 2 plus Fibonacci of 1. So when we call a Fibonacci of 2, Fibonacci of 2 is already present here, so it's 2, so it will not go inside this calculation mode, rather it will return from the table. So it's the value 2 plus Fibonacci of 1 is also present in the table, so it's 1. So this will be 2 plus 1, 3. And then Fibonacci of 2, it's again in the table, so we don't calculate it, because when a Fibonacci of 2 is called, memory of 2 is equal to minus 1. No, memory of 2 is now 2, so it will be returned from the, so return memory of 2, so that's 2. Then Fibonacci of 4, which is nothing but Fibonacci of 3 plus Fibonacci of 2, so for Fibonacci of 4, now it will be 3 plus 2, that is 5, and then Fibonacci of 5 is Fibonacci of 4, which we have already calculated, and then Fibonacci of 3, so Fibonacci of 3 is this part, so memory of 3 is, I did not update the table, so memory of 3 is 3 and memory of 4 is 5. So now to calculate Fibonacci of 5, we need Fibonacci of 3, so when we have n is equal to 3 here, so it will check the memory of 3 is equal to minus 1, but memory of 3 is not equal to minus 1, so it will go here and then it will return memory of 3. Memory of 3 is 3, so it's 3, and then 5 plus 3 is 8. So if we look at the top-down approach and a top-down approach with memoization, we see that Fibonacci of 2 is calculated only once and never again. Fibonacci of 3 is calculated only once, so it's here, and here it's not calculated, rather returned from the memory, so it was something like return memory of 3, so that was 3 here, so it was not calculated. So number of additions we have is 1, 2, 3 and 4. So number of additions here is equal to 4. Number of additions here is 1, 2, 3, 4, 5, 6, 7 additions, is equal to 7. So if we look at the dynamic programming approach, we had a problem. So it was Fibonacci of 5, and then we had a recurrence relation, that is nothing but if n is less than or equal to 1, then 1, otherwise Fibonacci of n minus 1 plus n minus 2, from which we got subproblems. That was again Fibonacci of 4, Fibonacci of 3, Fibonacci of 2, and then Fibonacci of 1 and 0. And we recorded the results in the table, and we solved each subproblem only once. So if we look at the subproblems like Fibonacci of 2, it was calculated only once, Fibonacci of 3 calculated only once, and for rest, for example here Fibonacci of 3, it was returned from the table. So we calculated the result only once, recorded the results of the subproblem to the table, and finally we got the solution to the problem of Fibonacci of 5 is equal to 8 using the table. So that was the memory table that we used. So this was a simple example to show the top-down approach using the dynamic programming style.